So we're going to compute a line integral through a vector field. This is our first example. There's a video that explains the theory behind this. It's called The Idea of a Line Integral Through a Vector Field. You can watch that first. But the way these are typically given to you, you're given f, which is your vector field, which assigns a vector to every point in the space you're working in. Today we're just looking in the 2D plane. So here's the vector field. So for example, if you were to say what's f of, I don't know, say you put 1, 2 here, then it would give you back the vector 1 squared I minus 1 times 2 times j. Well, that's really just the vector 1, negative 2. So if you were to draw the xy plane and you went over to the point 1, comma 2, this is 1 and up 2, the vector you'd get there would be the vector that would go forward 1 in the x direction, down 2 in the y direction. So it would look like this purple vector. That's what it would look like. And so what this vector field would continue to do is for every point in space, make a new vector using the formula that is on the right side of that equation. Okay, and so what we're going to do now is we're going to move around a path. Our curve C is going to be a quarter circle whose equation is this: r of t equals cosine of t times I plus sine of t times j. And you may be familiar with this parameterization for a circle, but this is how you do it. This circle will start off, depending on what your values of t are, but for this problem, we're going to restrict t from 0 to pi over 2. And you might say, why are those numbers? Well, if they're giving it to us. If you plug in 0, the cosine of 0 up here would be 1, and the sine of 0 would be 0. So this would correspond to t equals 0. If you plugged in pi over 2, let's underline a different color here in red, then the cosine of pi over 2 is cosine of 90, which is 0, and the sine of 90 is 1. So you'd land up here at the point 0, 1, and that would correspond to t equals pi over 2. And so what you're doing really is you're moving along this quarter circle path in this direction, and every point along the path is going to have a vector associated with it determined by this crazy thing up here. So that's what you have. Okay, so it looks like we have all the pieces and we're ready to go. So we learned in the other video that a line integral vector field looks like this: integral over the curve C, f of r of t dot r prime of t dt. So in our case, f of r of t means you're going to take this equation and sub it into that vector field. And so wherever there's an x, you're going to put the cosine of t. That's going to go in for your x's. Wherever there's a y, you're going to put sine of t. So let's do that. So this integral, our vector field is x squared minus xy. So x squared is going to be cosine t quantity squared I minus x times y minus cosine t times sine of t j. So that's that vector. That takes care of just this part. And then there's a little dot for dot product. So we do a dot product, r prime of t. So r prime of t means, and I've written on it so many times, but here it is. It's this thing I'm circling in black. So that's r of t. So r prime of t means you just take the derivative of it. So r prime of t, the derivative of that cosine would be negative sine of t times I plus cosine t times j. So that's what's going to go here. Negative sine t times I plus cosine t times j, and then a dt. And this is all going to go from 0 to pi over 2. Okay, so this is actually an integral in a single variable. The only variable you see here is t. So we just have to finish that off. So that's what we're going to work on now. So in case you forgot about dot products, you multiply the x components together, you multiply the y components together, and then you add them up and see what happens. So that's going to be our plan. Something pretty nice happens here, actually. When you multiply the two red ones together, you get negative cosine squared t sine t. And you put a little plus. That little plus comes from the dot products. That's what the dot product says. You multiply the x components and the y components from each corresponding vector, and then you add them together. So that's where that plus is coming. And then over here, interestingly, you also get another negative cosine squared t sine t. So that's actually pretty nice. So this integral just becomes the integral from 0 to pi over 2. There's a negative. If you want, you could put it out in front or not. It doesn't matter. So let's say I leave it there. I get negative 2 cosine squared t sine t dt. Now it's just a matter of evaluating this. Okay, so this is really like a chain rule in reverse. You can use a U substitution if you want. How did I spot it? Well, what I noticed is I have it's right here, the cosine function inside the squaring function. So I'm going to make this way, negative 2 cosine t squared sine t dt. So that's not a bad thing. All right, so let's suppose you can use the U substitution here if you want. It's up to you. Let's say you did. Then u would be cosine of t. Du dt would be negative sine of t. Or if you want, we can write that as dt equals du over negative sine of t. So now I'm going to plug this in here. I'm going to plug that in there. I'm not going to worry about the limits of integration for now, although I could change them if I wanted to. I could, if I want to, I can plug the 0 in here for t and do math like that. I don't know. I'm going to just do this and I'll plug it in at the end. So if I rewrite this integral, just ignore the limits of integration for now, you get negative 2 u squared times sine of t times du over negative sine t. And this very nice thing happens. The t's cancel. You kind of know if you did a U substitution right, if you get rid of your original variable. That's the whole point of it. And then this negative 2 and this negative 1 will cancel to a positive 2. So you end up with 2 integral u squared du. But that's just 2u cubed over 3. Don't forget u is really cosine t, so this thing becomes 2/3 of cosine t quantity cubed. We're going to evaluate this from 0 to pi over 2. Okay, so if we take the time to plug pi over 2 in there, we get 2/3 cosine pi over 2 quantity cubed. And you know the cosine of pi over 2 is 0, so this whole first term is just 0. So 0 minus, we're going to have 2/3 of cosine of 0 cubed, but cosine of 0 is just 1. So cubed is 1. So you get 0 minus 2/3 or negative 2/3. So we won't worry so much about the number as much as the fact that it's negative. The fact that it's negative here means is that the vector field was worked against us as we traveled along this path. It did negative work to us. We didn't get any help from this vector field. So it was like walking outside on a windy day and the wind was blowing on your face the whole time. Okay, very good. Thanks for watching.